Here we go with part B. Let's represent f of x equals sine of x as a power series where c equals pi over 4. Now we're definitely got ourselves a Taylor series because we are not centering at 0. And I just wanted to write again the definition of the Taylor series, where our coefficient there, the nth derivative of our original function evaluated at c over n factorial. Okay, so the way we're going to begin, really, it's all about that numerator. The other parts are just going to follow. I mean, we could right now fill in the c, n factorial n, no problem. This is what changes from problem to problem depending on your function and depending on where you're centering. Okay, so we're going to start with that. We're going to look at the original function evaluated here at pi over 4. Okay, well, sine of pi over 4 is root 2 over 2. Then we're going to take a derivative. These derivatives much easier than the previous problem. First derivative is cosine. Let's evaluate that at pi over 4. Hey, that's also root 2 over 2. Okay. Let's take a third derivative and evaluate it. Well, now it becomes negative root 2 over 2. I think I went all the way to 5 derivatives. And sorry, that's so tiny you can barely see that, the fifth derivative right there. Why did I go this far? Well, because sine, it's got this cyclical derivative, right? I eventually wanted it to double back on itself, and then I decided to even just go one further. So we've got the sine and cosine kind of, we see the full cycle, and even one more. And that'll be clear why later. Okay, so when we evaluate, we've got our second derivative is negative root 2 over 2. Our third derivative with cosine, also negative root 2 over 2. Our fourth derivative goes back to positive. And maybe you can see why now I did a fifth derivative, because we get that second positive. So if we did a sixth derivative, we'd hit the negative. So it does this like 2 positives, 2 negatives, 2 positives, 2 negatives, kind of a pattern. Okay. So these are what we're after. That tells us all of our numerators. Let's fill this in, and hopefully it all fits. I think I just got it to fit on the screen there. Let's try and keep everything. Okay, so following our Taylor series definition, at n equals 0, well, n equals 0, 0 factorial, x minus c to the 0, and you notice I filled in pi over 4 for the c. And we got our numerator there, square root 2 over 2. So we're filling in each of those parts. Okay, then this next one, I've got my numerator here, and n equals 1 factorial raised to the first. Then we went negative, so minus that over 2 factorial, x minus pi over 4 squared. Okay, and for n equals 3, I use my third derivative value, negative, sorry it's so fuzzy, root 2 over 2 over 3 factorial, x minus pi over 4 to the third. N equals 4, we're back to positive here, 4 factorial to the fourth. N equals 5, still positive, root 2 over 2, 5 factorial to the fifth. And we can tell, and I don't think we need to do anymore, the next two are going to be negative the way the derivatives play out. So a couple things fortunate here in just the cyclical nature of the derivatives. Also, none of these are 0. And we kind of prefer non-zero. Sometimes zeros, it's almost like you did that step and you're like, oh, like that was a waste, because that's not going to give me anything when I get to this point, because it's going to vanish Obviously, it's not a waste, but it kind of feels like, we want these non-zero terms. That's what reveals the pattern. Okay. Well, let's go ahead and clean this up as best we can. So let me get rid of these other numbers where we don't need those anymore. What's going on here? So first thing, you notice that every term has this root 2 over 2. Well, instead of simplifying those 2's with those denominators, I'm just going to pull root 2 over 2 out of the whole thing. And boy, this sure gets a lot cleaner with those root 2 over 2's gone. I also did simplify the 0 factorial and the 1 factorial. But I kept the 2 factorial and everything from then on. So, and sorry, it barely fits on the screen and it's kind of blurry there. Oh, I actually put a bracket on the end after the ... Yeah. Okay. So if I was asking, on a test for, maybe the first 3 or 4 non-zero terms to this, you could stop right here. You could have even stopped previous to that. But what if I was asking for the pattern? Let me try and keep this all on the same screen as I go to the next page. So building off that right there, it turns out this is the pattern. And most of it isn't too bad, isn't too hard to figure out. One aspect of it is pretty challenging. So f of x will equal, well, we've got that root 2 over 2, so that's just outside everything. Let's go ahead and start at n equals 0. Let's skip this part for the moment and just look at the easier parts. So the difficult part is the positive, positive, negative, negative, positive, positive. How do you represent that? We've never seen that before. But if we look at the simpler parts, well, right, 0 factorial, 1 factorial, 2 factorial, 3 factorial. We could think of that piece as 1 over n factorial, and then of course we have x minus pi over 4 to the n. No problem there, right? To the 0, to the first, to the second, to the third, along with the factorials of the same value of n. Okay, this part is actually a lot of fun when we are in class together. How do you represent positive, positive, negative, negative, positive, positive, negative, negative? And it's cool as a class to kind of guess and check your way there. Sometimes a class will get it, sometimes not. In the end, here's one way to do it that works pretty nicely. If you want positive, positive, negative, negative, positive, positive, negative, negative, do this. Negative 1, and really we knew that, but what do we raise it to? Raise it to the n times n minus 1 over 2. So that way, if n equals 0, well, the whole thing is 0, and you get a positive. If n equals 1, plugging in 1 here also gives you a 0, making the whole thing positive. But now as soon as you go to n equals 2, you've got 2 times 1. When you divide by 2, it turns it back to an odd number, and you get a negative. At n equals 3, you've got 3 minus 1, which would reduce with that 2, and you'd have it to the third, and you end up fitting this neat pattern of the doubles. So now that you've seen this in an example, if you ever come across it again in the homework, positive, positive, negative, negative, then you'll know what to do. Perhaps you might even come across a question that starts with negative, negative, positive, positive. Then there might be you'll need a slight adjustment here to make it start at negatives. But I'm going to leave that to you if you should happen to come across it. I'm not even sure that you will. Okay, but of course, maybe on a test I would just have you leave it as in this previous style. Okay, we're going to stop this video here. In the next video, you'll need to have that handout ready about halfway through it. I will see you there.